I'm not going to spend a lot of time in data processing because I think Martin's going to do a much better job with a kind of a demo. But I did want to illustrate the type of typical data processing workflow that we used to go through. So you do all your field stuff, you'd collect your data, you'd pull the various data streams off the aircraft or off the sensor, and then you'd put them into typically a proprietary data processing routine. And out of that routine you'd get a point cloud, and that point cloud would be for every one of the flight lines that you flew. But then that's where a lot of the work and a lot of subjectivity in the workflow starts. And this, I'm not going to go through all of these steps, but this is typically what we would do. So we'd have some tile set up, we'd set up a project, we'd bring in the flight lines, we'd do some bundle adjustments or matching of those flight lines. We do some quality control to get rid of high points, low points, so on and so forth. And then we'd probably get into filtering the data, do some ground classification or classification of other data attributes. Then we would output the data to some intermediate format. Then we'd probably do some raster modeling on the data. Then from that raster modeling, we'd probably end up with digital elevation models, canopy models, and so on and so forth. And so that's where we get to there. That would be a typical workflow, but there are many variations on that workflow. Just to illustrate some of these steps graphically, here we're setting up a tile array for a project. Doesn't matter where this is, but it happens to be in northern Saskatchewan. This is a large watershed, the White Gull watershed, and you can see each one of these coloured strips is a flight line. So I can't remember how many flight lines that is, but it's in the I can't remember, but in the 50 to 100 flight line range. It's a lot of data, a lot of flight lines. So the data set will be tiled, and the reason it's tiled is because we can be dealing with tens of millions or billions of data points, and we typically can't handle all of those points in one go, so we have to batch process everything, and so the batching is based on a tile by tile basis. For the kind of workflow we would adopt, we needed to use the trajectory information to refine the flight line adjustments, or to bring the flight lines into alignment more precisely in post-processing. In order to do that, you need the platform trajectory information. So that's what you can see here. So each one of these colors represents the platform position, or the position of the aircraft for each one of the flights. And so here we have 5 different flights represented. So the next step is to ensure that the trajectories, which you can just very faintly see, are tied to the flight line data in the point cloud. And that's all done through timestamps. All of the timestamps are accurately known. And so for any point in the aircraft trajectory, you can precisely register it to a point in the point cloud. So we need to go through some quality control. That can be absolute or relative quality control. Here we can see 2 flight lines. There's a large gap between them. There's a large misalignment, so obviously that needs to be addressed. So we can check the alignment, we can apply bundle adjustment. And then, there's this, in this particular software package, TerraSolid, there is a module known as TerraMatch, where you can adjust for positional offsets through GPS. You can adjust for pitch roll and yaw or attitude offsets, and so on and so forth. There are many attributes you can correct for, and this is the net result of that. So you might start off with, in this case, I think we can see three different flight lines, the slight misalignments between them. After a good bundle adjustment process, they should all come into alignment. And of course validation or ground control. So in this example what we have is a runway. We've flown a strip of airborne LiDAR data straight across that runway. We have already surveyed from one end to the other using traditional survey techniques, a control field, and then we will compare them. And typically what we'll do is we'll look at the correspondence between the data and map it according to the distance out from the point. So we'll have a control point, and then we'll say, well, within 10 centimeters of that point we observe this offset. But of course the closer you are into your control point, the lower the probability you'll actually have anything to compare to. So you need to keep looking further and further away from your control point. And so that's what we're doing here. We're mapping from 0 centimeters out to a meter. So you'll see, as you would expect, the offsets between the control data and the airborne data increase as we move away from the centroid of the control point. An illustration of ground classification. So we're trying to turn this point cloud into a ground and non-ground point cloud, so we apply some filter to that. This is what it looks like in cross-section in the TerraScan software. So here's a point cloud in an urban environment. We apply ground classification. That's what the ground classified point cloud looks like afterwards. So you'll see there's lots of data voids. And of course the idea is when you create a ground model from this, if it's a building footprint, you just assume it's flat and you interpolate straight over it. Or you can use those data voids as an index of where the building outlines are, and you can extrude buildings up out of those data voids. So the lack of data in this data set is actually very useful. The lack of data contains real useful information. Okay, so once we've done with the point cloud, now we can start modeling. The typical modeled product would be the DEM, but of course we can generate canopy height models as well. We can generate leaf air index. I mean, why do we care about these things in hydrology? Well, vegetation attributes influence friction, evapotranspiration, and all kinds of parameters within hydrological modeling or hydraulic modeling, so it is useful to be able to do that. We've already said we can track changes through time. The example here is observing canopy height change. We need to consider the way we will create our grids. We're going from a random, not a random, but a non-rectilinear point cloud distribution, and when we rasterize it, we typically want it to conform to some kind of rectilinear pattern. And so there are a number of things to bear in mind when we interpolate. I think the first thing to bear in mind is that for most of our applications, the data are as dense or more dense than what we want to model. So we need to think to ourselves, are we actually interpolating the data, or are we aggregating the data? In fact, I would argue most of the time we're aggregating the data using an interpolation function. I will not spend time on this slide, but just to illustrate the point, there are many different ways we can interpolate data. And within all of those different types of interpolation, there are many choices the user can make in how those interpolations are implemented. And here's one example. On the left and the right, we see a hillshade. Okay, it's not a particularly pretty hillshade, but it's a hillshade of a terrain somewhere in the world. And we're using exactly the same inverse distance weighted interpolation. The only difference, well, the only real difference between the two, other than a slight shift in resolution, but the main difference is, for this one we're using a 2 meter search radius, for this one we're using a 4 meter search radius. Now I should note that this is a very densely forested environment. More of the forest is on this side, and so what's happened here is the data density at ground level is much lower where we see the denser forest. And it's just low enough that when we use a 2 meter search radius, we're actually creating a lot of data voids. You know, basically 2 meter search radius is looking around and it's, oh, there's no point here, we're just going to return a data void. When we increase it to a 4 meter search radius, then all of the gaps are covered and the entire surface is created. Now we could have used a triangulation interpolation. We could have just triangulated a surface across all of this and we would have ended up with something similar to this. But you know, triangulation is a different type of interpolation. We may or may not want to use that. So the point that I'm illustrating here is that search radius matters if you're using an interpolator that requires a search radius. And just to take this to the absurdly simple level, just to illustrate a point, here we have a profile through a canopy. And we're asking ourselves, is the raster method important? Okay, well if we want canopy height, we might use a localized maxima. And so that's going to, the grid will conform to the nearest maxima point on that grid. But you can see here how there are differences between localized maxima, localized mean, and localized minimum. Now, of course, you're saying, well, of course they're going to be different. We've got a point cloud, we've got points lying on top of points. Of course, if we look at the mean, maximum, minimum, they're going to be different. But the point I'm trying to illustrate here is that these are different ways to extract rasterized information from a point cloud. They're intuitively different. But if we were using different types of gridding methodology, it might not be so obvious what the differences would be, but there would be likely different results that would stem from different types of either interpolation or grid-based summaries of that point cloud.